6, Newton's second law of motion, force and acceleration. Here's the big idea. An object accelerates when a net force acts on it. All right, remember we talked about acceleration. We said acceleration was a change in velocity over time, so over the amount of time that we had. Well, what causes that change in velocity or that acceleration? Well, that's force, and that's what we're going to talk about in this section, in this chapter. Force, unbalanced force, causes an object to accelerate. So when we have a force that is not completely balanced, then we're going to get it. So for instance, if we've got this hockey puck and it's sitting in the middle of the ice and not moving, it's got balanced forces. The force of gravity pulling it down, the force of the ice pushing it up, it's balanced, it's in equilibrium. But if we come and we hit the hockey puck, all of a sudden now it accelerates. So we put an unbalanced force on it with the stick. And let's say it slides along the ice and then somebody else hits it with another stick. They're going to put another force on that, and that's going to change the motion again. But every time that we accelerated that object, it was due to a force being applied. So remember, we're talking about net force. So the overall net force of all of those things. Remember, we talked in the last couple chapters about how the force can be broken down, or maybe there was a couple of forces acting on it. But we're talking our net force now is going to be what causes acceleration. And so if you want to increase acceleration, you need to increase the net force. And the acceleration of an object is directly proportional to the object's, or to the net force applied to that object. And that little squiggly line stands for directly proportional to in this example here. Okay? So if you kick this football, it was at rest maybe, you're holding it, then you kick it, and now it's not at rest anymore, and it doesn't move in a straight line. We've got all these forces now acting on it. So there's multiple forces. You applied a force when you kicked it. There's a force of gravity as it's moving through the air. So we've got all these multiple forces acting on that, causing acceleration to that particular object. All right, section 2 says, for a constant force, an increase in the mass will result in a decrease in the acceleration. So we're going to talk about how mass and acceleration are related. And, a good example is, think about, if you've got a shopping cart and it's empty and you're pushing it, that's pretty easy to do. If, on the other hand, you have it loaded, let's say you bought a whole bunch of dog food, you got 50 pounds of dog food or whatever in there, and now you try to push it, that same force does not accelerate it as much. It's a lot harder to get it to accelerate. So acceleration depends on the mass. Okay? So that's going to be our key part in this particular one. So last section we talked about how acceleration was directly proportional to force. Now we're going to talk about how acceleration is inversely proportional to the mass. Now, remember, when we're talking about directly proportional, if we're saying it's directly, we're saying as one goes up, the other one goes up. If we're inversely proportional, we're saying as one goes up, the other goes down. They are opposite of each other. So you can see if you increase the mass, you're taking 1 divided by that, and this number is getting bigger, obviously the acceleration is going to get smaller, and vice versa. So here's our elephant in the cart. Hey, he takes a whole lot more, force. So here's Chris pushing the elephant, and, pretty hard for him to accelerate that. Actually, that's probably not even an elephant. Probably a rhinoceros. I don't know what that is. Okay. So anyway, hard for Chris to push the cart, because he's not very strong. All right. So we're going to put these together, and this is Newton's second law, and it states that a net force on an object is directly proportional to the magnitude of the force, and it's in the same direction of the force, and it's inversely proportional to the mass of the object that you're accelerating. So here's my equation. The acceleration is directly proportional to the net force, inversely proportional to the mass. This is Newton's second law of motion. So remember, his first law of motion, we were talking about inertia. Here's Newton's second law. This is, it deals with acceleration and mass. And this is the formula that we will use. And actually, we'll probably, I always think of it this way, F equals ma, force equals mass times acceleration. And basically what we're saying is that, you know, if you increase the force, you increase the acceleration. You increase the mass, you decrease the acceleration in there. And usually when we do this, we're talking about force. We're going to talk about it in terms of newtons. Talking about mass, we're going to talk about it in terms of kilograms. And acceleration, meters per second squared. Those are my labels for this. So here we go, directly proportional, you know, as one goes up, the other one goes up, inversely proportional, as one goes up, the other one goes down, and, you know, we're using both of those, and we're talking about Newton's second law here. All right, so let's do this problem. If a car can accelerate at 2 meters per second squared, what acceleration can it attain if it's towing another car of equal mass? So what we have done was we have doubled the mass. So if we've doubled the mass, obviously we're not going to accelerate near as much. So our acceleration is going to be half as much. So it went from 2 meters per second squared down to 1 meter per second squared, if I am applying the same force on that. All right, here's a race car, mass of 1,000 kilograms. What's its acceleration if the force is 2,000 newtons? Well, you know, and we can use this formula, A equals F over M, but once again, I like this one, and this is where I always start, and then I kind of work figure out what I'm trying to get. So I'm going to say 2,000 newtons equals 1,000 kilograms times my acceleration. Well, that's pretty easy. We can see that the acceleration is going to be 2 meters per second squared. What if the force were twice as much? What if we had 4,000 newtons? Well, obviously, we're going to get 4 meters per second squared just simply by doubling the force. Same mass, double force, we're going to get twice the acceleration. How much force or thrust must a 30,000 kilogram jet plane develop to achieve an acceleration of 1.5 meters per second squared? So, you know, once again, F equals ma, mass 30,000 kilograms, 1.5 meters per second squared. Pretty simple math. 45,000, whoops, too many zeros, newtons. Oh, look, they got the right answer. All right, good for them. Okay. Now, we're talking about a force to accelerate an object. Well, anytime that you move something, there's this other force, this mean and nasty force, that wants to work in opposition to that. So we've got the force of friction, and that's what we're going to talk about now. Anytime we have two surfaces pressed together, we're going to have friction. It's usually caused because of irregularities in different objects. So if you've got two solid objects, you got irregularities between those two objects, it's going to move up and down, and it's going to take force to do that, or it's going to break those particles off, and either way that still takes force. And so there's always this friction force that slows everything down no matter what. And certain things are better at providing friction than others, and they're talking here about a rail, and it's actually easier to see if you have this picture. They're saying that nowadays you're seeing more and more of these concrete barriers because you get friction between the tire and this concrete, which is quite high, better than if you had this kind of a barrier and then you get the side of the car rubbing against there and it's metal on metal, and that's not as much friction, doesn't slow it down as much. So these kind of barriers are better than the other ones simply because they provide more friction, slow things down a little bit better. Now, if you're moving through a fluid, fluids are gases or liquids, anything like this. So air is a fluid, water is a fluid, anything that flows. Fluids are things that flow. And so we also have fluid friction. So we would have friction if we're talking about a car. We're going to have friction between the tires and the road, but we also have fluid friction as the car moves through the air. Or if you throw a football in the air, it's going to have fluid friction as it moves through the air. And that's air resistance is what we're talking about. Air resistance is that friction that we're talking about as an object moves through the air. And at low speeds and stuff, air resistance isn't much of a problem. You don't notice it much. You know, if you're walking, you don't really notice air resistance. On the other hand, if you're riding in a convertible going 55 miles an hour, you can notice a lot of air resistance as you move that. Or if you stick your hand out the window, you notice quite a bit of that. Well, when friction is present, we can have constant velocity. Remember last chapter we talked about, you know, hey, if you've got constant velocity, you've got no acceleration. And now we're talking about, well, to get acceleration, you have force. But, you know, we could be applying a force and actually get no acceleration because there may be another force acting on it. So let's say we've got this object here, and we're applying a force of 10 newtons. But, you know, because we're pushing it on the ground, maybe there's a force of 10 newtons opposing that force. Now, if that object was already moving, let's say that this thing, before, you know, I started, you know, before this 10 newtons, let's say that it was moving at 1 meter per second. Well, it's going to continue at that constant velocity, even though I'm still applying a force. Normally we would think, well, hey, if you apply a force, you're going to get some kind of acceleration. But the problem is, I am applying this force, but friction is counteracting that force. And so I hit this net zero force between those two things. And when you draw all of these forces, we call that a free body diagram. So a lot of times, you know, one of the key things to be able to do is to be able to take your object that you're talking about and figure out what are all the forces coming into play on that object, and you know, how do they react. So here's our, you know, Haley pushing the box. She's pushing it this way. Friction is opposing her, and obviously it's or maybe not obviously, but I mean it might be moving at a constant rate, but not actually speeding up, despite the fact that she's applying force. If you drop an object, you know, at some point, if it falls far enough, the air resistance is equal to the force of gravity pulling it down. And when you have done that, you have reached what we call, or we'll get to here in a little bit, called terminal velocity. And so if you have this sack that's falling, you know, the weight of it is pulling it down, obviously, but air resistance pushing it up or resisting that, and that's causing it. One thing to note, and because I'm sure that there'll be questions about this, but anytime that we're talking about friction, it is always opposite your movement, or opposite the direction that you're moving. So it always opposes motion. That's the way friction always works. Always opposes motion every time. All right, so two forces act on a book resting on a table. Its weight and the support force from the table. Does a force of friction act on it as well? Think about that. Well, what did I just say? I said that friction always opposes motion. Was there any motion in this book if it's just sitting on the table? No. So unless the book tends to slide or does slide across the table, friction forces occur only when that object tends to slide or slide. And what they mean by tend to slide, if I actually tip the table so that it was at an angle, so there is a force trying to pull it down, then friction would be opposing that force and going